Okay, I'm going to talk about digital radio modulation that Bidel and I have been playing with. Some of this is really fairly introductory material into modern radio coding stuff. That's mostly because I'm kind of a rank beginner in this. I've been doing digital radio modulation and decoding stuff for almost 3 years now. Some of you probably have more experience in this than I do. So where I make a mistake, please raise your hand and let me know. I'm sure Bidel will not feel shy at all. Like I say, I haven't been doing this very long, and a lot of this was new to me just a couple of years ago. And so it's been a huge amount of fun for me to learn about an area of software and hardware design that I kind of didn't even know existed, and have gotten to relearn a lot of the maths that I did in school when I was an undergraduate, and got to redo a lot of interesting software design methodologies as well. A lot different from my day job as a systems programmer, and so a lot of this stuff was a huge amount of fun. I used to kid Bidel when we started on this project that his hardware designs were simply a way for me to get a huge amount of fun building embedded software. And I was really grateful for him spending all of his time slaving away, constructing hardware so that I could go have fun building software. And then unfortunately, he suggested that maybe I should help out with some of the hardware designs if I wanted to try my own little project. And now I'm desperately hoping he'll want to take over some of the drudgery of software so that I can go build fun hardware. Yeah, we need more. We have a multi-level minion hierarchy. It's kind of the pyramid scheme of minionry. And so as you become more advanced in your minionness, you need to gain minions under you. Okay, I want to talk about modulation schemes, forward error correction, convolution coding, viterbi decoding in particular. And I have a short little section on the interleaving stuff as well that we're using. Most of the modulation stuff is a direct result of the hardware choices that we made, but the hardware choices that we made were informed by the fact that the hardware supported something we didn't think was crazy. There's a few important terms that I'm going to be coming across in my talk. BER, the bit error rate, it's the raw frequency of bad data. Usually expressed in magnitudes like 10 to the minus 6th or 10 to the minus 100th bits of error. Uncoded systems that don't use forward error correction like to talk in terms of things like 10 to the minus 1/3, 10 to the minus 2nd bits, error bit rates, and that's why we don't use systems without error correction. EB, the energy per bit, it's kind of the transmit power divided by the bit rate. So you've got 10 watts of transmit power and 100 kilobits, so you divide those two and you kind of get the amount of power per bit. I think it's measured in joules. I really had a hard time finding units for that, but that's the only unit that makes sense to me there. N0 is the spectral noise density. It's noise power divided by the bandwidth. So if your channel is 100 kilohertz wide and you have 100 watts of power, then you can kind of get the notion of how much power noise per hertz is the units of that. It's kind of watts per hertz. And the interesting unit that we use in most coding scheme analysis and most processing gain analysis is the EBNO number, the EB, energy per bit divided by the noise per hertz, the spectral energy density. And that kind of gives you a normalized notion of how good your coding system is, independent of the bit rate of the system and independent of the actual transmission technology. So if you're talking about, okay, so how good is my turbo code? The turbo code is going to be in terms of what's my EBNO number to get a particular BER, right? So if I have to have 10 dB of EBNO to get a BER 10 to the minus 5th, that's not as good a coding scheme as something which only requires 5 dB of EBNO to get the same error rate. Process gain. Processing gain is the improvements in the EBNO numbers from using a modulation scheme. So different modulation schemes like DSSS or FM or AM will have different process gains. And those are inherent in just the modulation scheme. There's no gain from additional transmitter power. There's no gain from fancy antennas. It's just you chose a smarter modulation scheme, you get to win. People who use things like on-off keying or AFSK, they get to lose because they chose a poor modulation scheme. So in this case, smart people get to win and use lower power transmitters and get longer range, like from Jupiter. Because Yeah, almost all of the stuff I'm talking here was originally designed to get data back from the Pioneer and Voyager deep space missions over the DSN, the Deep Space Network. The Viterbi decoding, the convolution coding, Reed-Solomon codes, all of that was massively funded by NASA trying to get pictures back from the orbit of Jupiter, which is pretty awesome. Okay, the other kind of gain I want to talk about is the other smart people gain. It's called coding gain. And that's the improvement in the EBNO numbers from using a better signal encoding. So that's just pure software. You don't have to change the hardware. You don't have to do anything. All you have to do is change your modulation and demodulation software bits, and you get to win. Again, another smart people gain. So here we have two basically free pieces of RF improvements that you don't need to do anything like put more power into the air or build a larger antenna array, which annoys your neighbors. All you have to do is be smarter about your beyond the receiver bits and beyond before the transmitter bits. And that's what I want to talk about is coding gain and process gain. Okay, frequency shift keying. Frequency shift keying is in the audio space is known as frequency modulation or FM. It's a pretty common technique. Why are we using that? Well, we're using that because that's what our radio chips do, and that in fact is pretty much all you can get in common off-the-shelf system radio chips. Trying to build a binary phase shift keying radio is really pretty hard because you can't just buy a binary phase shift keying transmitter without buying all the rest of the modulation stuff as well. Okay, very simple frequency shift keying. You get one frequency for a 0 and one frequency for a 1. Okay, so if you're switching that really fast, so once you're transmitting one frequency and then you turn it off and turn on another frequency, what are you generating in your RF spectrum? You're generating a pile of noise because you change the amplitude of one signal really fast, you change the amplitude of another signal really fast, and so you smear noise all across your spectrum. So raw FSK is kind of an unpleasant thing to do to the RF environment. So instead what we do is use Gaussian shaped frequency shift keying. And that's where you take one signal and just kind of slowly slide it over to the other one with this nice Gaussian curve. Like, you know, get a nice little bell curve and it goes back up. So it goes shoo, shoo, instead of going click, click. It's really not any different from a receiving perspective from regular FSK. All that it does is reduce the amount of noise you put in the RF environment, reduces the RF bandwidth that you need in order to transmit the signal. And so it's kind of the nice thing to do. It's like, why would you use regular frequency shift keying when your transmitter supports Gaussian shift, Gaussian modulated, or Gaussian shaped frequency shift keying? The process gain for frequency shift keying, and in fact any FM system, I could not get a beta in this font, and I'm really annoyed with that, so I'm using capital B here. Please apologize. The process gain is B squared, where B is just the ratio of the deviation. So if you're deviating by 5 kilohertz deviation, divided by the modulation bandwidth. So you have if you have a 10 kilohertz signal and a 10 kilohertz modulation, then your process gain is unity. You don't get any gain. You don't get any win from that. If you're deviating by twice as much as your bandwidth, then you get a factor of 4 in processing gain, which is pretty awesome. 6 dB just by making and what's that doing? It's making your signal wider. Okay, this term explains why we use preemphasis in traditional FM signaling. What is preemphasis? Preemphasis is where you amplify the high frequencies of your FM signal, right? And roll off the low frequencies of your FM signal. The reason that preemphasis is getting you better process gain is those high frequencies are very hard to encode. And so by amplifying those high frequencies, you're getting more process gain for the high frequencies of your regular FM signal. So that's why preemphasis in the FM environment exists. And that's why you hear hiss on an FM radio, because for exactly the inverse reason, that white noise is being, the high frequency noise is being amplified because your process gain for that area is actually is less than unity. And so you get a bunch of noise coming into the system. Okay, so frequency shift keying is pretty good because you get this process gain. You only get the process gain if your raw signal to noise ratio of the signal is about 10 dB. Right, so the carrier to noise ratio of your raw FM signal needs to be at 10 dB before you start getting any process gain. And that's why for a really weak signal, you don't want to use frequency shift keying, because with a really weak signal, your raw signal to noise ratio is less than 10 dB, and all of a sudden your process gain starts to turn into process fail because you actually start losing your FM capture, and all of this disappears and your FM signal goes into the mud and you get no signal out. Okay, what's another really common modulation technology? It's called direct sequence spread spectrum. People have heard of that? Yeah. It's a really simple, fairly simple technology. You take your signal with a pseudo-random noise sequence, usually at a really much higher frequency than your signal. Usually, it should be a fraction of your actual carrier frequency in order to get things lined up correctly. The chip rate is the rate of this pseudo-random sequence. And then you just multiply or XOR the two values together and modulate the carrier with the result of that. If you're using frequency shift keying or to smear the data across a wide spectrum, this is usually actually used with binary phase shift keying. And again, you take this really high frequency signal now and modulate your carrier with it. What does that do to your bandwidth of your signal? It makes it really wide. And is that typically good if you would have a really wide frequency? No, your receiver has to have a really wide carrier. All the noise gets added in. But what happens is when you demodulate that, you basically collapse all of that bandwidth back down to your original signal, and you take all the noise. I've got a lovely picture in a minute here, I hope. Yeah, I think so. I'll show you the picture. The demodulation effectively divides the noise by the chip to bit rates. So your process gain turns into this chipping rate, which is the speed of your pseudo-random number, divided by the bit rate of the original signal. So if you have a chip rate of a megahertz and a bit rate of 100 kilohertz, you're getting a process gain of 10, which is pretty awesome. Again, all you have to do is be smarter about your software. There's no difference in your radio. You're just modulating faster. So another win for smart people. Binary phase shift keying is almost always what we use with direct sequence spread spectrum. You just have two symbols 180 degrees out of phase with each other. And so a 1 is this signal and a 0 is this signal. And how do you tell the difference between those two? Well, you kind of modulate them so you can. So you're only interested in where the phase shifts, and that gives you a signal between 0 and 1 because you can tell where the phase shifts, but you can't tell what the current phase is very easily. The process gain of this, of course, is the chip rate over the data rate. Okay, why aren't we using this? This seems like the smart people encoding technique. Why doesn't Altus Metrum use this? We can't get parts that do this. So we may have to build our own custom silicon NEC so we can do direct sequence spread spectrum. Because this is clearly, for digital radio, this is the only one you would really want to use. This is what cell phones use. This is what digital TV uses. This is what satellite communication uses. This is what everything uses. It's clearly the right plan. Here's the picture of what, can you see this at all? Almost, yeah. Okay, so here's how direct sequence spread spectrum works. You start with this narrowband information signal, and then you multiply it by this, or you XOR it with this really high frequency pseudo-random sequence, and you smear your signal over a huge swath of bandwidth, but the amplitude is lower, right? Because the amplitude, you've taken your signal and you've divided it out over a whole much more space. And so your amplitude is lower. Now I'm going to mix in some narrowband noise right here. Oh, you can't see my mouse, I apologize. Mix in a pile of narrowband noise. And the awesome part is when I demodulate, I actually take that narrowband noise and I multiply the signal again by the same pseudo-random sequence. What does that do to my narrowband noise? It spreads it out over this huge spectrum. What does it do to my original signal? Oh, I'm multiplying back in that pseudo-random sequence, which gets rid of all of that noise and gives me only my low bandwidth signal again. And so I've got this huge amplitude of the signal and a very tiny amplitude of the noise. Kind of pretty awesome, huh? That's where the coding gain comes from, the process gain in direct sequence spread spectrum comes from. You can get rid of these spikes, which means that direct sequence spread spectrum radios are very immune to jamming. Because if you just give me a huge carrier spike in the middle of my signal, I don't care. I can receive it anyhow. Another one that I'm not going to touch on very much is audio frequency shift keying, and that's where you take an audio signal and you put it into the mic input in your radio. So this is the old AX25 disaster, where you'd actually take an audio signal out of a Bell 202 modem and feed it into your FM transmitter. Well, if you feed it into your single sideband transmitter, you're just taking an audio signal and muxing it with your transmit signal, and that just turns into frequency shift keying. So that works pretty well. So people that were experimenting with this kind of stuff with HF gear and SSB were like, hey, this is pretty awesome. We're getting credible performance by just feeding audio signals into the mic inputs of our SSB radios. And then the people tried this on FM. And on FM, it's kind of a disaster. With FM, you end up on the wrong side of your process gain on FM because the frequencies of the Bell 202 signals are really close to the frequencies of the actual the deviation, and so you end up getting very little FM process gain. Okay. And of course, the last one I just wanted to mention was on-off keying. This is really bad. We just key the transmitter on and off. Usually they use Gaussian shaped keying on and off. If you ever, who does CW? Anybody play with CW? Yeah, I don't believe you, BDO. Yeah, moon bounce. Yeah, okay. And that uses on-off keying, and of course it's lovely because you have a very low data rate and a really simple transmitter. The problem, of course, is that you have a very broad spectrum because you're keying again a transmitter on and off, and you get no process gain at all. But in a weak signal environment in the FM world, you don't get any process gain anyhow. But anybody who's doing anything clever in moon bounce should be using what kind of modulation scheme? Binary phase shift keying with a DSSS. That would be the only sensible plan.
No, you should use Joe Taylor's code and just forget how it works.
Yeah, whatever. Probably true. Okay, so that's all I'm going to talk about process gain and modulation techniques. So we all learned that the radios you can buy do Gaussian frequency shift keying, and it works okay as long as you have a signal-to-noise ratio of better than 10 dB. If you don't have that, if you're in a much weaker signal environment, you want to use direct sequence spread spectrum with binary phase shift keying. Pretty simple. We now want to talk about forward error correction. I know there are a lot of people that have built digital radios that don't use forward error correction. They're insane. Don't listen to them. Just nod and say, "That's very nice, dear. I'm glad you have a radio." But anybody doing anything sensible in digital radio is going to use forward error correction because, again, it's free gain. It costs you $0. It costs you just a bit of software. And so all that forward error correction does, of course, is add extra bits to the data. You add a bunch of redundant information to your signal, and then on the reception end, you can look at that redundant information and help it regenerate the data. There are a bunch of different forward error correction techniques. I'm only going to talk about convolution codes because that's the only one I've implemented. I read up a bunch on turbo codes, and I think I almost understand how turbo codes work, and they're basically concatenated convolution codes. So it's very similar notions, and a lot of the things in convolution codes also apply to turbo codes. The other error correction technique that I know that I've heard about a bunch about is Reed-Solomon coding, and those are much longer block codes, and I wish I understood how they work, and I just don't. It's kind of sad. Maybe someday I'll have to implement Reed-Solomon codes. That's the one thing I've learned in my engineering career is until I implement something, I have no idea how it works. I can read as much as I want about something, and until I actually go and write it. So how did I learn about languages? I wrote compilers. How did I learn? how did I learn about graphics? I wrote graphic systems. Yeah, it's kind of a low-level and very tedious way. So
just keep learning about new things.
Yeah, that's just because BDL gets more toys out of it. So one of the big things, so forward error correction is to be able to recover data at lower powers, and that lower power levels. That's obvious because we're getting free gain here. So I can use the same transmitter and the same receiver and get a reliable data channel at lower power levels. I can survive impulse noise. If you live in any place on a continent, there's going to be an aircraft radar system around you somewhere. And when that aircraft radar sweeps over your area, it's going to give you a nice big spike of RF energy in the middle of whatever packet you were trying to transmit. Using a little bit of forward error correction, you can kind of notice that there was a big spike of IC in the middle of your RF data and correct right through it. And that's one of the keys to forward error correction. Convolution coding is what I've done. That's because it's what the CC11 did or does, and what the CC1120 does not do. There are two common kinds of convolution codes, the non-recursive, non-systematic codes. A systematic convolution code is one which replicates the input in some of the output bits. So a systematic convolution code, if you had a perfect transmission, you could just throw away all the error correcting bits and extract the signal directly from it. The original signal bits would appear in the output. A non-systematic code doesn't have the original signal bits appear anywhere in the output. They're usually used and that's what I've implemented is a non-recursive, non-systematic code. The recursive systematic codes, that's what turbo codes use. So a turbo code is basically two convolution codes that are using a recursive systematic convolution. Recursive means that you take the output from some stage of the convolution Wait a minute. Yeah, I have some more pictures here to show how convolution. You take some output and feed it back in. You provide a little feedback within the encoder. The rate, there are two terms, the two relevant terms for convolution codes. The rate, which is the ratio of the input to the output bits. Almost all the convolution codes anybody uses anywhere these days take one input bit and generate n output bits. So we talk about 1 over n convolution coding. If you throw away a random or a collection of those output bits, you can generate convolution codes that have an effective bit rate of some other fraction. So if you were generating 2 output bits for every input bit and you threw away every third output bit and just discarded it and used error correction to recover that data, that would be a 2/3 rate convolution code. The constraint length is the other important part about a convolution code, and that's the number of output symbols that are affected by a single input bit. And output symbols, by output symbols I mean a collection, however many outputs bits are generated, that collection. So in a constraint length 3, rate 1/2 constraint length 3 encoder, which I'm going to show the example of here, you have 6 bits generated for every 3 bits input. So 1 bit change on the input can change any of those 6 bits on the output. So that's what the constraint length means. After that constraint length, a change in the input bits can have no effect on the output because the constraint that's what the constraint says. Constraint length for non-recursive encoders are really easy to understand. You just look at the number of bits that are being put together. They're not recursive. For recursive ones, it's a bunch more maths. I haven't quite figured out how those work. Someday, maybe. Maybe I'll have to implement one when I do turbo codes next. This is why we use convolution coding. This is a coding gain chart that I stole from, borrowed from this freely available Theory and Practice of Error Control Codes paper. You can see here, so on the vertical axis you have the EBNO number, the probability of the BER. This is the probability of an error. 10 to the minus 6, 10 to the minus 8th. So that's the number of, that's your bit error rate. And on the axis down here, you have your EBNO number. So this is in dB, not as a ratio. And so you can see that as you want to have a more and more reliable channel, which is to say as your BER gets smaller and smaller, then your convolution code is giving you more and more gain in that environment for the same EBNO number. So at typical stuff, like you want 1 bit in a million error. And so your convolution coding gain from that, I can't see this at all on my screen either. For 10 to the minus 6, you have a coding gain of about 2 to 3 dB for a convolution code. This is a bunch of different convolution codes you can see down here. The rate 1/2 constraint K, that's the one that I'm going to give you an example of here. So it's that green line. It's the worst one, but it's the simplest one to understand. And the rate 1/2, it doesn't have the rate 1/2 K equal 4, which is what the CC1111 uses, but it's somewhere in there, 2 or 3 dB. Again, free gain for just doing clever software. Here's how a convolution coder works. S0 and S1 are just little delay boxes, so that's like it saves the previous bit and passes it along. It's just a shift register. So you hand 1 input bit in. So you initialize S0 and S1 to 0, push a bit in, and generate 2 bits out. And then you just wash, rinse, and repeat. And so as you can see, after 3 bits go through this encoder, it doesn't have any memory beyond 3 bits because it only has 2 pieces of memory in the shift register, and then the bits get dumped into the usual bit bucket. Here's what the CC11 uses, the rate 1/2 K equal 4 non-recursive coder. You can see here that bits are different, and they're only different in the fact that so the operation down here that I'm showing is just XOR. It XORs all the bits together. So you can see bit 1 and bit 0 have a different collection of bits being XORed together. The bottom bit gets all 4 XORed together, and the top bit just gets 3 of them. So they're slightly different in the output. Okay, how does this matter? You've got this crazy encoding. What's this going to do? Well, what it does is it constrains the output. It constrains the output so that when you have a particular sequence of input bits, you get a different collection of output bits. Of course, I'm going to skip over that one and explain the trellis diagram here. If your previous state was 0, 0, so S0 and S1 both have zeros in them, and you get a new 0 bit, then your new state is going to be S0, and the convolution encoder, which you can see here, this is the one we're working with here, if S0 and S1 were 0 and you put a new 0 bit in, what are bit 1 and bit 0 going to be coming out? They're both going to be 0 because I'm XORing a bunch of zeros together. If the previous state of S0 and S1 were 1, were both 1, and I stuck in a new 0 bit, then the output of the convolution encoder is going to be bit 1 will be 1 and bit 0 will be 0. So the output bits, bit 0 and bit 1, depend upon not only the current bit, but the previous 2 bits as well. And that's what this trellis diagram shows here. It shows that if you were in state 0, 0, and you got a 0 bit, then you would transmit 0, 0, that's the bit 1 and 0 numbers there, and your new state would be 0, 0. If you were in state 0, 0 and you got a 1 bit, then you would transmit 1, 1, and if you go look at the little XOR thing, you'll note that both of the bits turn to 1. And your new state would be 0, 1, because you just shift. Remember, you're just shifting bits into the S0 and S1 state. If your state was 1, 0, and you transmit a 0 bit, blah, blah, blah. You can see, so those are all the 8 different transitions. Each input state has 2 transitions depending upon the next bit, and you get to a new output state. Okay, so that's a simple little trellis diagram. And that's going to help us explain how decoding this thing works. Decoding it is kind of fancy. I know that convolution codes were developed in the 60s and 70s, and I know that people were using other algorithms other than the one I'm going to describe to decode them before then, sequential convolution decoders. I have no idea how they work because in the 70s, Andrew Viterbi figured out that a cute little software hack that he put together could effectively decode these. And he knew that it wasn't as good as the existing massively cool state-of-the-art hardware that other people were doing because he'd only invented it himself, so it wasn't very cool until somebody proved that it was optimal and all the other techniques disappeared. The shy engineer. Andrew Viterbi went on to help found Qualcomm and invent CDMA and do other cool things. So he's an awesome guy, except for the fact that he works in patented stuff. And so we love him for having actually released the description of the Viterbi coding, for Viterbi decoding for convolution decoding, and we hate him for locking up CDMA at Qualcomm. So, you know, some people go astray. What? Yeah. So Viterbi decoding turns out to be provably optimal for decoding convolution codes. But it's important to realize that Viterbi decoding and convolution encoding are really very separate notions. Convolution codes can be decoded in a number of ways. This algorithm happens to be optimal. It has another really cool features. It's a small piece of code. I think my decoder is 30 lines of code. It has fixed memory requirements. That is to say, once you specify the code, you have a fixed amount of memory needed in order to decode arbitrarily long input packets, which is awesome because that means you can build hardware to do this, which is always nice because hardware is always faster than software. NASA built a massive Viterbi decoder for one of their deep space missions that was, I'm trying to remember, it was like a rate one quarter K equals 8 encoder with like 16,000 states to decode this thing. And they built hardware for that because they could. It was fixed amount. Sometimes large, but yeah, fixed in any case. So what does the Viterbi decoder do? At each node in the trellis, remember our pretty little trellis diagram, you measure the distance between the symbol you received and each of the 2 possible transitions. So if you are in state 0, 0 and you see a 0, 0 symbol coming in, then you know that the measured distance from that to, oh, that must have been a 0 on the input, is only 0. But the distance measured, let's go back and look at the trellis diagram. Oh, that was it. So if I'm in state 0, 0 and I receive 0, 0 on the input, then the distance from that symbol to the transition to new state 0, 0 is 0 because I received 0, 0 and the expected value to go to state 0, 0 is also 0, 0, so the distance there is 0. But the distance to get to state 0, 1, where I would have expected to see a 1, 1, that distance is 2. And so you just keep measuring those distances. You sum the distances all the way across through the whole packet. And then you choose the path with the least distance from the received path. And that's how it's kind of provably optimal, right? You've got the path with the least total error through the entire reception. There's two different kinds of Viterbi decoding. You have hard decision, where you have just where your receiver only gives you ones and zeros. And then you have soft decision, where the receiver says, I'm not really sure what that was. It was more like a 1 than a 0, so I'm going to say it's 0.7. Soft decision is awesome for frequency shift keying, because what does your FM demodulator give you? Your FM demodulator actually gives you a frequency between the two bounds of your modulation, right? It says, that was 0.7 volts instead of 1 volt or 0 volts. And so your frequency shift receiver automatically gives you these soft decision values, as long as you can bother to get the hardware to hand them to you, which the hardware that we're currently using is very reluctant about. The benefit of using soft decision is that you get about 2 dB in additional coding gain over hard decision. And again, guess what? That's free. You just have to have software that does it. There's no additional transmitters or receivers or antennas or power supplies. It's free receiving power. When I discovered that our hardware did not have any support for, or did not have nice support for getting soft decision data out of it, I wrote a little note off to the manufacturer and said, this part is awesome, fabulous transmitter, awesome receiver, but I don't get any soft decision data except 1 bit at a time per interrupt. And the manufacturer said, yeah, you should just use the hard data. It's way easier to get. And it's like throwing 2 dB on the floor? I don't think so. How many interrupts can my processor take per second? And it turns out that the STM32L is quite happy to take 1 interrupt per bit. Okay, so here's a description of what a larger trellis diagram looks like when receiving correct data. You can see here the input bits that I have here, and these are the outputs of the encoder, right? So here's my receiver. Here's what my receiver is getting. So my transmitter, the original input data here into the transmitter is at the top line, and the next line down is what the convolution encoder generated. And then I'm going to walk the trellis diagram, and I drew out the state transitions and the costs associated, the error costs associated. And again, you're summing the error costs all the way across. And so every time you see a state transition that increases that number, then that state transition had a cost. And again, those state transitions are the difference between the expected value along that path, which I'm not showing here, and you can only see in the original trellis diagram, and the actual symbol that was received. These slides will be available. This diagram I drew myself. So in this particular one, all the input symbols I received were exactly correct, which is awesome, because that means it's actually kind of boring, because that meant my receiver was too close to my transmitter and I wasted a bunch of transmit power, which is never good, right? But as you can see, the cost for this bold path through the trellis diagram, which shows you the state transitions that I'm making through the system, the costs are always 0. And so you get to the right-hand side, you notice that there's a 0, and then you just follow that line back to the input. There's a unique path back to the input, and that's the data that you were transmitted. And so the receiver shows you what you got out of the output. Pretty simple. Here's what happens when you get a bit lost, just 1 bit lost. In this particular case, the second word here is received as 10 instead of 11, which is what was actually transmitted. And you can see here that in this second case here, you have 2 states that both have exactly the same cost. You got a 10 instead of a 11, and the receiver's like, heck, I don't know. It could have been a 1 bit. It could have been a 0 bit. They look the same to me. And so you have the same error cost. And so at this point, if I stopped receiving at this point, that would be an ambiguous piece of data. I would have no idea what the correct data would have been at that point. But I'm going to receive another bit. Now I've got this new 0-1 bit. And in this case, the 0-1 bit, if it's a 0-bit transition from the 10 to 00, then the cost of that is 0, because that's a valid reception from that point. But here, in this other one that also had 1 error cost, if I got a 1 bit, that also would be a legitimate transition from 11 to 11. And so the error cost of that is also 0. And so you can see at this point I'm still confused. I have 2 states that both have cost of 1. because of this one bit failing up here. And at here now, we finally find out that this one, the two possible state transitions that it could have received, both of them would have cost more than 0. And so both of them would have a cost more than the correct one in the middle there, this 0, 1 state here. So you can see that the decoder caught up after a couple of possible ambiguous bits. If you get more errors, then the length of time that it takes to recover from them is even longer. But you can see here at the end, it's still pretty clear. You have one path back that has a cost of 1, and then you have other paths back that have higher costs. And so it's pretty clear you follow that one back all the way back to the beginning. And so that's really how that's how a Viterbi decoder works. It decodes the entire packet, and it starts at the end and walks its way back to the beginning to pick out all the correct bits. There are optimizations involved where you can say, oh, you know, I don't have to go all the way back to the beginning. I can start partially decoding the data after I've gotten a bunch of bits in, and it's unlikely that older bits will have changed. Okay, I implemented this in software. What? Okay, I've got, 2 more slides. I implemented the obvious algorithm. The obvious algorithm was first decoding packets at a rate of about 1 packet every 1 second on my STM32L. That was probably not going to be good because I'm transmitting 10 packets a second. I optimized that for days. Got down to 14 milliseconds, almost 15 milliseconds per packet. I read Phil Karn's most excellent software implementation with SSE and MMX acceleration. You can Google for this FEC 3.0.1 code that was from 2007. I meditated over that code for days, and I looked at the source code and I said, how does this work? It's totally Martian code to me. I wrote a lengthy email to Phil asking him a number of questions about how his code worked. And as soon as I'd finished writing the email, I understood how the code worked, of course. I went off and implemented the improvements, and now the thing decodes it in about 5.7 milliseconds per packet. So I have transmitting 10 packets per second. I'm decoding in about 6 milliseconds. So I have plenty of overhead. Oh, and that 5.7 milliseconds per packet, that includes 1 interrupt per bit coming out of the receiver. So I'm taking 38,400 interrupts per second to get the soft decision data out of the receiver. There's one more thing I'm going to talk about, interleaving. Why do we do interleaving? The problem with that Viterbi decoding and the trellis diagram is if you smash a whole long sequence of bits in a row, it can often just get totally lost. If you smash more than the constraint length of the code, you will probably never recover. And so in my k equals 4 code, if I smash 5 bits in a row, I probably won't get that packet decoded. The nice thing, what you do with interleaving is you take the output of the encoder and you mix up the bits in some way. The CC1111 does it regularly. I've learned since that turbo codes do it in a pseudo-random way in order to mix the bits up so that they don't get even disturbed by periodic noise. And mostly the goal here is to reduce the impact of impulse noise when you're decoding stuff, because the Viterbi decoder is really good at fixing single bit errors as long as it has a couple of bits to recover. But if you have a long sequence of broken bits, it sucks at that. This is how the interleaver works. You put bits in one direction and you just pull them out in the other direction. And again, these are after the encoder because you need that pair of bits to be aligned together. You don't want to be interleaving individual bits because you want to smash both bits together or get both bits correct. Here's what we're doing with the CC1111. BDL talked about this. It's a rate 1/2 k equal 4 convolution encoder, soft decision Viterbi decoding. It's exactly what we wanted. Here's what and so of course all that we did was choose that transceiver and then set some other parameters. The symbol rate, the input symbol rate of 19.2 kilobits, the encoded rate of 38 kilobits. Of course, it's a half-rate encoder, 20 kilohertz deviation for about 100 kilohertz channel bandwidth. Nothing too magic there. The chip loved it. Then we switched to this new chip. It doesn't have an encoder. It doesn't have a decoder. It doesn't do interleaving. And its soft decision data is available at the stunning rate of 1 bit per interrupt. Please don't drop an interrupt because that bit will be gone. It's got a single the register. It has a single register holding a single value. And overall, FEC is free. All it costs is software, and everybody knows that software is free. That's why we write free software, right? GFSK isn't the best encoding available, but it's widely supported in COTS hardware, and when you stick competent FEC on top of it, you get a pretty awesome radio. And that's all I have time for. Questions? I thought I had till 11:30. Yeah?
Obviously, basically half your signal capability for error correction.
Right.
Are there other combinations where you're willing to sacrifice more to get more signal through, potentially losing more error or gaining more error?
Yeah, of course. So right now I'm doing a rate 1/2 code. If you want to have a higher error rate, you can use a rate 2/3 code or a rate 3/4 code. And the closer you get to unity, in other words, the fewer parity bits you're sending, the higher the basic error rate is going to be for a particular EBNO. Yeah.
So I love when Keith says things like, if you want a higher error rate.
You're willing to tolerate a higher error rate.
Yeah. So I just, every time he says that, my brain kind of goes, yes, the issue here really is, if you're trying to receive signals from the orbit of Jupiter or something, then it really might be worth transmitting a lot of bits per bit to get marginal improvements in the coding gain, where by marginal I mean fractions of a dB. But in almost all practical systems, almost everybody out there uses rate 1/2 codes, because it turns out that with interleaving, that covers, it makes it's one of those things where a little bit of FEC makes a huge
difference.
A lot of FEC makes a small incremental improvement.
And again, the coding gain is over the uncoded data at the native data rate. So when I talk about a 3 dB coding gain of the coded data over the uncoded data, that's not over the same channel. That's if I have to double the bit rate in the transmitted data, I still get, that's the coding gain I'm getting from that coding. So even if I have to double the modulation speed or have the data rate, I still get that coding gain. So it's not that I'm, if you just double the bit rate, you're going to get, your EBNO numbers are going to be divided by a factor of 2, because your energy per bit is divided by 2. But the coding gain is above that. So it takes that into account already. So you transmit twice as many bits, but you're doing forward error correction. So you're losing 3 dB in your energy per bit, but you're gaining that back plus more by the coding gain, which is just awesome.
So what length impulse before you start actually getting some serious transmission that's interfering with it?
It's usually related to the D-free number of the code, which I didn't describe at all. And the D-free number of our codes is 5, I think. And so if you smash more than 5 bits, you will not get that packet will not be transmitted correctly. We put a 16-bit CRC on all the packets, of course. And so we check some of the packets when we get them down, and so we throw away ones that have had erroneous transmissions. Yes, of course. And in fact, our UI displays the number of CRC errors in the received packets, so you can tell how many have been not correctly decoded.
It's completely normal to go through an entire rocket flight and have that number never go non-zero.
Right.
But the objective is you might have the signal strength drop way down, and you might lose the ability to receive it all. But if you're receiving it all, you ought to get it back.
Yeah.
With that, say thank you to Lito and Keith.
Thanks, guys.